Okay, for the other people here, I wanted to go and at least get you guys sort of oriented in terms of the first exercise and sort of how that's going to be going. I know that we probably have commitments, need to get going. We'll go and work on this tomorrow. When you get here, you can start working on the exercise as you get here. And again, I sort of want to get you oriented together because you'll probably trickle in tomorrow. That if you go and take your exercise book, we're going to be starting at the very beginning. And we're going to be going and where it says RPV, okay? And we're going to be doing that sort of pre the program, trying to go and generate the LFP V8 spreadsheet, okay? So we're at the very beginning, or if you go to the first picture, which is this one here, we're going to be doing the stuff, which is to pick the end members on the logs. Instead with the RPV tool, we're going to be doing it by hand, okay? And what you're going to need to do is that Mark Locke ended up printing out two different wells, the Batavis and the Scaffold well log. In fact, the Scaffold was a well through the gas leg of that amplitude I showed you that appears on the cover. And what you're going to need to do is to go through and play petrophysicist and pick some of these generic sands and shales. And one thing though that we have done at times to make your life a little bit easier, hopefully he's got that one here. Let's see, does he have the if you take a look at, and this is for instance the particular Scaffold well log, that the stuff over on the left-hand side is sort of a composite of all the well logs to sort of help the sort of uninitiated. That you can go and see here, yellow means sand, the blacker areas end up meaning shale. And what would be good to go and take a look at is to go and understand where your particular sandy levels are, okay? Another way of being able to identify the sand is to go and take a look at the gamma ray over on the right-hand side, because shales are radioactive, sands are not. And so enhanced levels of sort of radioactivity are going to be indicative of a shale. And if you actually look at the gamma ray log here, you end up seeing that there ends up being more activity in the gamma ray right through here where it corresponds to the shaly interval, okay? And so based on this, you need to go through and take a look and identify what the particular density and the sonic are. And also if you take a look here, that the particular density log ends up being one of the particular curves coming down in this column, and then also the sonic log ends up coming down here. And so what you're going to need to do is identify an interval, let's say right here where you see a good sand, or right here where you see a good sand, and also pick a couple of the obviously shaly intervals. And then from there go and pick what you think the particular sonic and density is for those two intervals, and record that in one of the particular spreadsheets, okay? And we have two different logs. One is going to be Scaffold, and the other one is going to be Batavis. The one thing to know about Batavis, I'll just sort of tell you right off the hand, it's the one with some good brine sands in it. Scaffold ended up going through the gas leg, okay? And for those of you that also aren't used to going and looking at these logs, but probably are used to thinking about CSEM, gas is resistive and brine is not, right? And so one of the logs on here is a resistivity log, so an indication of the fact that you have gas and not brine comes about from the resistivity, okay? And so to go, take a look at this. Again, gamma ray tells sand from shale. Resistivity tells you gas from brine, and then look at the sonic and density in order to be able to pick off what those values are for those sort of end members, okay? And so just come and pick these up, and then once you go and figure out each of these wells and what your particular intervals are on them, I'm going to need to sit down here and sort of show you here on the screen some stuff. Let's just go to Control Alt QI frame. Now, this is going to be a fairly critical folder, and all of you have the QI course exercises. If you double click, we have folders for each one of the exercises sitting out here. You go and open up exercise 1, and there will also be the LFP V8 exercise 1 sitting in here. And also, if you want to take a closer look at some of the well logs on here, you can always double click. We have a well log viewer, and you can actually look at them a bit more carefully here and sort of blow them up if you want to. But the main thing that you're going to want to go and we talk about bringing in is the particular LFP V8 exercise 1. Always say enable macros. And we've made it easy here for you. And what you're going to need to do is to fill out sort of the top and bottom of the measured depth of the interval that you pick in each of the wells. You need to go and say what the lithology is. And these little corners here end up meaning there's a comment. And if you hover over it, it will go and show you what the comment is. And for instance, here you'll see the lithology code is 0 for sand and 1 for shale. So when you pick a sand interval, make sure it's 0. And a shale interval, you want to make sure it's 1. You can go here if you think that it's a good or a probably okay or questionable sonic. You can go and put in here that quality code. You also can put in the sort of the most likely sort of value in that interval, a high and low value in that interval. I'll also show you in a second what that sort of comes about and what we mean by that range. This is in DT and microseconds per foot. Those are the units on the well logs. It's actually 1 velocity, and we sort of go with the flow with respect to the petrophysicists and what they like. You also can go in terms of the shear log and pick out what the particular values are for the shear sonic, and also when it comes over to the density log, what the values are for the density. Over here that you'll need to go and estimate what we call the low frequency interval velocity is, but we have a little button in order to calculate that, and we're going to be talking about that a lot later on. And when it comes time to press that button, I'll go and sort of talk to you a little bit more about it. And also you need to go and estimate what the invaded zone fluid is in terms of its velocity and density. And this will be where you're going to have to go and guess on whether or not it's, well, by looking at the well logs, decide whether or not it's a gas or a brine, and then put in the appropriate value according to that, okay? And then you want to put in your initials here. And you will need to go and fill these out for each one of these, because the other subsequent spreadsheets will go and sort of complain about that. And once you've gone and filled this out, that you'll need to then go into the particular analysis spreadsheet, which is where we do the cross plotting. And we'll tell you to go and load that spreadsheet that you just filled out. Shouldn't be showing you this. It's already open. doesn't like the fact that I already have that other document open, so I'll need to close it. So I'll close that, say load the data, open that. It actually loads that data in, checks it, and then you can go over here to the graphic output, and it will start showing that data actually cross-plotted for you, okay? And I know that you're probably saying, okay, now you've sort of told me a lot, how am I supposed to go and remember and know what some of the instructions are? That if you actually go in here into your exercise book, they're actually written out sort of step-by-step instructions. For instance, you're going to ask, okay, what should I go and put in for the VP and the density if it's gas? Well, if you look at point number 2, it tells you what those values are, okay? And so this is a bit of a follow the bouncing ball, okay? You follow the bouncing ball of what it's telling you to do. If you have any particular questions as you go through there on philosophy of what you should be doing, ask me. If it really looks like a lot of people are getting stuck or have the same question, I'll go back up to the screen and explain some of the things, okay? But I also will go and allow you to go and struggle a little bit trying to do it and figure it out, and then go and show you afterwards. And don't worry about struggling a little bit, because I think it makes it so when you finally see, me show you, how it should be done, that it ends up, I think, sticking a little bit more. So I do allow a little bit of struggle before I'll actually show you the way through the forest. But by the end of the course, many parts of this, when we hit the last exercise, hopefully you build up enough facility to be able to start walking through those steps yourself. And then one last thing I sort of want to talk about, which is what sort of these high and low values are that go in there. And if you're looking at one of these well logs, and if you go and are sort of picking one of these sections, okay, and let's say that this was sort of the particular, let's say, sonic response that you're looking at, okay? Many times what I'll do is say, okay, here's a good shale, here's the top and base of that shale. Here's, let's say, is another good shale. There's the top and base of that shale. And, okay, here's another particular, let's say this is a nice sand. Here's the top and base of that sand, okay? Then the next thing that you go in and do is say, okay, if I now go in, this is sort of the P50 value, this is sort of the high side, and this is the low side associated with that, okay? And how does that show up? Well, that'll show up as the size of this error bar, okay? It's that the middle value will be here, and the top and base will show here, okay? So that you get an idea of what the fluctuation is within that particular interval. Then you also do the same thing here and the same thing here, okay? And in fact, the RPV program, if you just tell it the top and base, it actually calculates those 3 values for you, okay? And that's the reason why the petrophysicists, have gone and worked and sort of automated the process, okay? Should we go and pick this as a good sand? What do people think? Okay, we should. Why not?
Doesn't seem representative of things.
Okay, well maybe it's just not very sandy. Okay, another thing that could be happening here. What do you think another thing that could be happening?
You don't have a lot of samples, so you can't accurately calculate a P50, P90, P10.
Yeah. Well,
It's responding to some other.
well, is this thick or thin? Do you think that it could be thinner than the resolution of the log tool?
Yes.
Okay. If it is, the tool itself is going to be averaging some other thing in there. Okay. So it's another thing to make sure that things, okay, are thick enough to be resolved by the well. Okay. And so this is a no because of that, more than likely. Or maybe it's just a thin laminated package is another possibility. Okay. Okay, another thing, should I have gone and, let's say, picked this interval? Well, what do you think? Is that a good choice? Okay, no, okay. Well, what's probably happening there?
It's probably a fining downward sequence, so it's a mixture of sands and shales, agnes, silts.
It's not an end member, right? Okay, it's a mixture, okay? This is probably a mixture, okay, and should not be picked, okay? In fact, by knowing this is probably where your end members are, actually picking a little thing there actually may not be too bad, okay? But, you know, many times if this was a finding upwards levy, even at the base, you could still be only 50% net to gross. But what you probably would see in that case is something which goes like this if there's a finding upwards levy. And it would never get close to what the end member is, okay? You know, John, you have a question, go ahead.
So, this picking stuff, given your goal is to essentially establish a whole bunch of different, of I guess rocks, or consistent but separate collections of properties.
Yes.
Can be done using statistical tools, like there's like t-tests and things for establishing whether things belong to the same distributions or not.
Yeah.
So shouldn't this be automated?
No.
No.
Let me tell you that.
Well,
There's a lot of reasons, but I've tried that. You'll see more tomorrow
Right.
because there are laminated rocks, and they consist, if you look at cores when you see them, and I'll show you a picture of that tomorrow. They consist of these kinds of end member materials.
Yeah.
Laminated together in different concentrations,
Sure.
so that what you will see in your statistical test is a continuum of properties in different intervals, but in fact, it's really, the end members are really quite sort of separate, and if you actually look at the logs and various log responses, you'll recognize the end members, and some core to go with them. You'll recognize end members, and you'll recognize those that are composite rock, what we call composite. Wait till tomorrow, and we'll talk some more about this.
Yeah, no, it's a very good question, and it ends up being, you know, it's one thing that's really is part of the BHP style is to go in and pick these end members. The thing is, it's very fast compared to, you know, going in and trying to understand the whole log and then exclude something on the basis of other logs or other criteria. And it turns out that, you know, per well, I mean, I think you're probably going to be lucky to get a half dozen picks of good end members in one well, especially for sands. Most of the time it's only 2 or 3. And so that you also now are suffering from very low statistics, because if there are only 2 or 3 points out of 10,000 that are actually the ones that you should be looking at, you suffer from having good enough statistics to be able to separate them out. But I think, though, as Dave has said, that the sort of the simple answer is sort of no, but again, we'll get into that as time goes on.
There's another reason, John, and I'll bring it up here. I talked earlier about looking for sport rocks and what have you, and Mike reiterated it in a different mode by saying, look, when you see an outlier, and you go back to the log and say, yeah, it's there. I picked according to all the rules. It's thick enough, and that's what the log is reading. You better try to understand what that means. When a human being is looking at the log, the human being can put the red flag up, okay? That program has a lot more difficulty picking that up and considering the possibilities. And when it only takes one mistake that cost $1 million to drill that well into a dry hole, where you'll wish you had looked at it.
So do you include sport rocks into this analysis? Yes. Okay.
Yes, and in fact, if you took a look at, I flashed by it fairly quickly, but if you took a look here at the lithology, you know, volcanic, anhydrites, carbonate, you know, we have 3 unknown. You could use that for coal. And these are really labels, and you can just use a different label for each of the rocks. We ended up only supporting these as consistent ones at the time. But that's exactly right, that if there is a sport rock, you should trend the sport rock. And it's a really important, the reason why we accentuate this actually has come through a lot of look-back studies. The biggest mistake that we make in petroleum is not by not understanding what we think is going to happen. It's by not considering something that does happen that we never even thought of. You go and drill it, and you never thought it could be a coal. You never thought it could be a volcanic. You never thought it could be low saturation gas, and you never even risked it. Okay, and that is the biggest mistake of not expanding or thinking of all the models. And that's one reason why I always, at the very beginning, and something that geologists, you're very good at, is thinking of possibilities. And I highly encourage, especially in the early stages of analysis, think of all the possibilities and have a rational reason for eliminating those possibilities. Because that's how, at least in petroleum, we end up failing a lot. And it's probably the major failure of those. In fact, people even commented, the last paper that we published in the Leading Edge, that the comments we've gotten back from certain Norwegians that are reading it, was refreshing that you admitted so freely how you really screwed up. and how we really screwed up in this case was focusing so much on the economics of if it was a sand, we never even thought of the fact it would just be a soft shale. And we went back and had to revise the paper rather heavily with an interesting little epilogue. But people found that, again, refreshing, but it's also a very important thing if you go and read through that case history of how we do, a major way that we don't always consider what we should. So. I'm sorry, it's sort of a long answer, but I wanted to go and amplify a bit on it because since it is such an important sort of failure mode for us in terms of our analysis.
I have one thing for you guys. I know you're just eager as beavers, and so tonight when you're having your gin and tonic and you don't have anything better to do, take this with you, and you'll find in here a little tab that says Pop Quiz. And then there's another little tab after it that says Pop Quiz with answers. There are 2 pop quizzes in there, and you can, based on what you heard today, you can take both pop quizzes, and if you're lazy and really having your gin and tonic, you can sort of skip the pop quiz and just look at the pop quiz answers because the questions are repeated in the answers. So you can look at the answer sheet and just read those things. But it's good to read the questions first and just see, do I know that? Do I remember that?
Well, if this would be a PTC health and safety induction, you'd have to get 100% on the pop quiz, and we wouldn't allow you out of the room right now. Now, it's an interesting thing. After they give you, sort of, did they give you a quiz after you had your induction?
Of course.
A group quiz.
Yeah.
Well,
Well, they
one
actually
answer-
give you personal quizzes at PTC.
Well, that's what they-
One
So you
answer
have
seemed to
this-
suffice for the group. Exactly.
It was rather interesting. After I saw my first one, they said, "Oh, here's your test." It's like, what? But my last test was back in graduate school, my very last course. Okay. So anyways, you can come and collect the well logs, and if you want, just get in and you can start when you get in tomorrow morning. We'll go and start at 8:30 tomorrow. We'll probably give you about 20 minutes or so on the exercise starting that time, maybe as much as a half hour to work through some of the parts. And you are welcome to stay today or get in a bit early tomorrow too, if that's your preference too. But right now we're going to have to make sure things are kept moving, so I'll probably get moving on after about 9 o'clock tomorrow. We'll have to get going on the first lecture. So, okay?
Sam, you just want to flick the paper over for the password.
Scene is really quite involved in doing a good job in terms of getting the pics, and to sort of show you a bit about where we're going. And at that point, I'll sort of poll people on whether or not you would like to go and continue to dig into this, or whether or not you feel that you've gotten most of the advantage out of understanding how we go and pick these intervals, okay? Because we are flexible and we can go and give you a bit more time to dig into this for another 15, 20 minutes. Let me sort of go and we can turn your attention up here to the screen. And I want to go and show you first is that there is an answers folder on here. And you can go and double click on here and you'll have the same PDS files that you've been working on. But what you end up seeing is that the interval that was identified by the petrophysicists who originally worked on this are shown here. And this line goes from the top to the base of this genetic interval that was picked by the petrophysicist. And also you see what he ended up picking as his low and high side. I think his middle value was always halfway in between those two. You also see where these things are indicated on the density, the sonic, and also it's shown on the shear sonic, what the values were that were picked. So that when you get to a particular point and you've worked on it, you can take a look at this. I do have to say that Mark Locke, I saw, was taking quite a bit of care going through and picking the intervals here. And he's an experienced petrophysicist at doing this. I can almost assure he probably picked different intervals and has a modestly different interpretation. So I may end up going, and after he takes a look at what Glenn did, we may even have a little bit of an offline discussion and then come back on and even talk to you a little bit about some of the particular choices on this. So that's one thing I wanted to go and inform you about here. The second thing is those particular picks have been put into, again, a spreadsheet, and that actually appears in the answers section. And so that one thing to caution you on is that it actually wanted these measured depths in feet to be sort of consistent with the trends. The logs are in meters, and so you'll end up seeing one of the sort of the conversion problems. This is an Excel spreadsheet, so you can go and use and put in the conversion factor quickly. That's 3.28 between the two. That more is filled out here than needs to be. But you can go and see that this ends up being a shell convention in terms of P10 to P90. All the numbers should be low to high. DTs are in microseconds per foot. You will go, and the spreadsheets are smart enough, they will correct you if those aren't in the right order. And also for the density, it goes low, medium, high in these intervals, okay? And also, there's a low frequency interval velocity, and I'm going to talk quite a bit about this in 2 lectures. But let me just sort of tell you what it ends up being right now and what sort of happens when you end up hitting this particular find button. The first thing is the first time that you click this, it will take a little while because it's starting up the MATLAB program behind the scenes. Until it loads it the first time into memory, it'll go and will take just a little while in order to do it. So don't be concerned with a little bit of a delay. You can see that MATLAB, if you sort of stand up and look at the bottom of the screen, down here it's actually started up now. And so it now is all taking a little bit of time reading in the well logs. And what you end up seeing and what it's done is taken the sonic log and has gone and smoothed that with about a 300 meter average, which is roughly equivalent to seismic resolution in imaging velocity picks, okay? And then it's gone at each of the measured depths that you've selected, okay, has gone and picked off what the value is from this smooth sonic log and has filled in those particular values for you, okay? And right now you're saying, why on earth would you want to do that? Think about it a little bit, and we'll have a fairly extensive discussion, again, at the 2 lectures from now, about the logic behind this, okay? And the next thing to note is that after you go and bring this in, there's another particular spreadsheet, the LFP analysis spreadsheet, which is the first spreadsheet that actually does something. We have 2 types of spreadsheets. One is a data spreadsheet, and the first one that you're entering in is one of these data spreadsheets, okay? This one is a spreadsheet that does something. It doesn't keep data, it goes and works on data, okay? So it's like an application is the way to think about it. And so the first thing that you want to do is go and load in your data, and I'll ask you where that data is you want to load in. I'm going and picking this. It says finish checking data, 0 errors found, okay? Now, if you would have gone and had one of these DTs in the wrong order, it would have flagged that for you and highlighted those cells for you to correct, okay? And then after you go and do that, if you would go back into, and if you end up having some errors in this particular spreadsheet, let me go back to the main spreadsheet. If you had errors, you could correct those errors and then just say check the data again. And it will show you the particular remaining errors. You can go and also go and load trends, and that here we ended up having available some global reference trends that have been fit against a fairly large database. And now if I go to the graphic output, that you can go and take a look at, this is the sonic velocity versus depth. You see that these points don't fit very well. Well, this ends up being sort of an average value for the Gulf of Mexico. And we'll talk a bit in 2 lectures about why this particular, sort of velocity versus depth trends ends up being the most local trend. But you do go and see that if you look at the VP versus VS trend, which ends up being the most robust correlation, that the particular points all lie within, or except for this one point, within about 2 standard deviations of the sort of expected value. And also if you take a look here at the particular VP density relationships, that everything goes in this point and lies within those particular sort of error bounds with respect to the global trends. You do see that the shales on average lie a little bit higher than you would go and expect. Now, if for instance you ended up seeing one of these points that didn't look, let's say, quite right, and let's say that, let's say this particular point right here, let's say that I sort of felt was sort of near the edge of where it should be. If you click on that, in fact, with the idiosyncrasy of Excel, you might have to click on it twice. Then if you go up here, it says find point, it says Control F. If you go and hit Control F, it'll tell you where this particular point is, which well, what depth. Then it'll ask and see, do you want to go and see where that point is? And if you click yes, it'll highlight that row so you can go and take a look at what that point is, okay? And it turns out at this point that if you went and put in the initial gas density, which ends up being 0.24, okay, which was the initial value here. And now if I looked at where the things were in terms of that graphic input, let me go back here again. The that you'll go and see that if I had the initial density, this thing is sort of sitting way out there and outside the bounds of where you actually think that that particular sand should be. And then if I would go and then click on that again, that it will go back and refer and then do the Control F. It refers back to that particular point. And I could see that that was having this particular value, which ends up being, this was the outlier, okay? And just sort of ask, okay, this is an outlier if I put in the true gas density, but if I ended up putting in this 0.85, okay, or this larger density, that it ends up coming on and is more consistent, okay, and ends up falling right on the trend that you would expect, okay? Let me sort of ask people, well, why do you think that, that it ended up not giving you the right value if I ended up putting in this 0.24 for the invaded zone fluid, but 0.85 grams per cc thick? Any suggestions from the audience, or?
Yeah, a mixture of gas and water.
There's more of a mixture of gas and water. There's more water there than what you would have expected for a gas zone, okay? Can people go, and does anyone know anything about a resistivity tool? And does it read very deep or very shallow compared to a sonic log?
It can read. It
What?
can read deep if you go for the deep resistivity.
Right, if it's a deep resistivity, right. But but many times what we go and read with ends up being that the deep resistivity, I'm sorry, but if you go and look at the density log itself, is that a shallow or deep reading tool on average? It's a shallow reading tool, right? Okay, so it reads more shallow than the sonic tool would read, right? Okay, so what could be happening around the wellbore? So what we're sort of saying then is there's more water close into the wellbore, okay? So what could be causing that? Yeah, the mud fluid, okay? This is drilled with water, so water can get in close to the wellbore. And Tim, you're right, that you want to take a look at the different resistivity tools and understand that and put in what you feel that the effective fluid was that was actually sensed by the density tool. And it also goes and sort of points to another thing. If you're going to go and make a synthetic, okay, off of a well log, okay, that you do need to make sure that you correct for any invasion effects around the wellbore, because because what the particular sonic will see, okay, or the also in what the seismic data will see is the uninvaded result, okay? It's not going to see the invaded result. And so again, whenever you go and form a synthetic, you need to take a look at the resistivity, understand the invasion profile, and make a correction for that whenever you make a synthetic. And it shows up here even when you trend, and that's why Dave said, well, go and try to trend with just the wet points, okay? Those are the really good ones, okay? But you can go and play these games to make sure that, the gas points do go and substitute back onto the line. And one way that you can play this game, and then we go back here to the main, is that there are a couple little things here, and we'll talk about this a little bit more in the next exercise. But one shows the Gaussman correction. And if I say don't correct, it just shows the reservoir points no matter what. It doesn't make any correction. It just shows them as the value as you read them off of the well log. But the problem is, if you look at the graphic output, that this ends up being way down here and sort of off of the line. And so if I go and say I want to go and Gaussman correct that, again, you see that actually goes and Gaussman corrects back onto the line. But if you had the wrong invasion fluid, if you had the wrong invaded zone fluid there, in other words, if it was really a mixture of gas and water, rather than pure gas, we saw that that point ended up being about where my cursor is, okay? So it's a nice way to play that game and understand what's going on. But also, if you went and saw this on your trending, it'd be a real, red thumb that if you're going to form any synthetics off of this, you better correct for invasion zone effects, because that obviously, right there is reading an invaded value, okay, in terms of what the well log is. Okay.
So do petrophysicists generally pick the trend curves? Or is that really left to the geoscientists?
My particular thing and the dialogue, if you talk with all of the Shell petrophysicists, they believe quite strongly that the trend curve should be picked by petrophysicists. I also feel that that is the case. Things have evolved here in BHP to where it ends up being the geoscientists that do the trends. But I really go, and it's a thing that I've talked with Gabriella about. I would welcome more participation of the petrophysicists in actually determining the trends. And it comes about from, and you'll see that there are things of really what are common rocks. And unless you've really gone and have intimate knowledge of the well logs, a lot of that things really come and slap you in the face. You go and see outlier points. Times that Andy Brickell has been involved in looking at things on trends, he immediately spots that, can go back, and many times will say, oh yeah, I either made a mistake or that is a different lithology. And it's better for the petrophysicists to make those calls.
I'd make a suggestion here in the middle ground in the environment you're describing is, look, you have petrophysical engineers, they got a tremendous workload, that's why the geoscientists are doing this, at least at first time in BHP. But a way to foster that cooperation is when you have a problem, you take your first stab at things, say, gee, I don't know why it's not fitting on the line, maybe it's an invaded zone, maybe it's not, how much would it have to be, do some calculation like Mike just did. Then you say, well, that might be that, but you're not certain, because you're not a petrophysical specialist. That's the point at which you could go ask your petrophysical engineer, I have an outlier, I have this, is this the cause of it? And that guy, that way you use their time efficiently and you get the best advice you're going to get. And also, you make the connection between people that...
This actually ended up working fairly well. I mean, that's exactly the way we've worked it. The QI specialists have gone and taken their first crack, have circled outliers and even circled where they are on the well logs, and then gone back to the petrophysicists with those small handful of issues, and then have had a dialogue. And that's actually been remarkably effective, and probably is why we've continued for 8 years with this working relationship. But the other way works very well too. So. What are people's feelings? Do you want to go and spend more time getting the points in yourself, or do you feel that you've gotten a lot of the value already out of the exercise, or? What's that?
I think press on.
Press on with
Yeah.
lectures, or?
Yeah.
Okay. But again, what I've seen a lot of good discussions, and you've thought about how you pick those intervals, and that's really what you need to get out of this. I welcome you going in and playing with the answers and the like during some of the other breaks. But we are going to come back to this. Okay. I'll go and switch over here to